Hello, welcome back to the NPTEL online certification course on deep learning. In our previous class, we were talking about how to train a fully convolutional neural network or a deep convolutional neural network to be used for semantic segmentation purpose. And we have seen there that obviously whenever we want to train a neural network or a deep neural network, we need a lot of ground truth data. So, for training a neural network to be used for semantic segmentation purpose, I need the original input image and the corresponding ground truth, which is the semantically segmented image. And when you feed that input image, what I expect is the output of the network will be a segmented image or semantically segmented image. And for training purpose, what we have done is this output map that you get, the output map has been represented as an array of one-hot vectors, where the dimensionality or the dimension of the one-hot vector is same as the number of categories of objects which are present within the image. So, if we expect that the image will contain 5 different objects or 5 different regions, then my one-hot vector will be of size 5. And you prepare your ground truth in the form of such arrays of one-hot vectors. And for training the neural network, obviously we need to define a loss function, so that using the backpropagation learning while performing the gradient descent training operation using backpropagation learning, then the loss function, the aim will be to have a gradient descent algorithm which will try to minimize the loss with respect to the network parameters. So, in your previous class, we have talked about a loss function which is pixel wise entropy loss. Today, we will talk about another loss which is known as dice loss, and after introducing dice loss, again dice loss is applicable for training the neural network which is meant for performing semantic segmentation. And then I will move on to another application of the deep neural network, the deconvolution network, that is the restoration purpose of a degraded image. And by restoration, what I mean is removal or filtering of the noise present in an input image. So, let us see that what is dice loss, and before coming to that, let me just recapitulate that what is an array of one-hot vectors and how using this array of one-hot vectors we have computed the pixel wise entropy loss. So, the array of one-hot vectors is something like this, that your output array is of the same size as that of the input image, but every element in the output array is now a one-hot vector, where if a pixel within the original image belongs to a region occupied by say horse, then in the output one-hot vector at the corresponding element, the component corresponding to horse will be 1 and all other components will be equal to 0. So, these are the one-hot vectors, or what are the target vectors. But what happens is during training operation, your network may actually output something else which is something different from this one-hot vector. So, by using your target one-hot vector and the actual output vector that you are getting, which is in terms of the probability that the pixel belongs to a particular category, in case of one-hot vector it gives you probability equal to 1, that the component corresponding to horse equal to 1, that means the probability that the particular pixel belongs to horse, that is equal to 1, and the probability that it belongs to any other category, that is equal to 0. That is what your one horse vector tells, whereas actually the network gives you some other probability measure. So, there is a difference between your target probability and the actual probability that you get, and using these two you can define a cross entropy, which is basically a measure of difference between your target and actually what you get. And this cross entropy loss can be minimized for training of the neural network. And the other loss that I was talking about, what is dice loss? The dice loss actually tries to find out that how much is the overlap between the target and actual output that you get. And this overlap is computed over every category or every plane. If I consider this array of 1 vectors, array of 1 hot vectors to be different planes. So, for example, this is a plane corresponding to car. So, this plane corresponds to car, this plane corresponds to horse, and so on. So, if I consider those to be different planes, then in case of this, when I try to compute this dice loss, what I do is in every plane I try to find out that what is the amount of overlap between the target and the actual array that you are getting, and based on this overlap you try to compute a loss. So, that is what is given by what is known as dice coefficient. So, it tries to find out the overlap which is in the form of A intersection B, where A may be your target array and B is the actual array that you get. So, if you take A intersection B and mod of that, that gives you the measure of what is the amount of overlap between these two. And if A and B overlaps exactly, then yeah, I'll have a maximum value or the maximum cardinality of A intersection B. And if I compute this dice coefficient in that case, obviously if they overlap exactly, then cardinality of A and cardinality B of B will be equal to same, and that will also be same as the cardinality of A intersection B. So, the dice coefficient, if you compute in that case, this dice coefficient will be equal to 1. Whereas, if you compute when there is no overlap, that means A intersection B becomes a null set and the cardinality of that will be equal to 0. Then whatever be the cardinality of A or the cardinality of B, your dice coefficient will be equal to 0. So, in one extreme, there are two extreme cases. In one extreme there is no overlap when the dice coefficient gives you a value 0, and when there is perfect overlap, then the dice coefficient equal to 1. So, when your target and the actual what you are getting, they matches perfectly, your dice coefficient becomes maximum, and when they don't match at all, the dice coefficient becomes 0. So, using this concept, we can try to define a loss function. So, in order to find out what is A intersection B, what you can actually do is you can multiply the two different arrays. One was your target array and the other one is the actual array in the same category plane, and you multiply these two, you get the intersection of A and B. So, that is what has been shown here. So, here A intersection B, you find that my actual target, if I consider that actual target is this is my target array, and this is the array that is given by the network. You multiply these two, then your A intersection B becomes this. And in order to find out the cardinality, you simply take the sum of all the elements in this particular array, and this array has been obtained by point-wise or element-wise multiplication of the components of A with the corresponding components or elements of B. And once I define this, then from here I can go for definition of the dice loss. So, dice loss, again, because I am computing this for every class, so dice loss can be computed for every class, and then sum over all the classes gives you the overall dice loss. So, here it is defined in this form. As we said, that the dice coefficient will be equal to 1 when there is perfect overlap or perfect match, and it will be equal to 0 when there is no match. Coming down to the loss function, if there is perfect match, my loss should be equal to 0, and when there is no match, the loss should be maximum. So, that is how this dice coefficient is computed over here. So, you find that the denominator of this fraction, this corresponds to mod of A intersection B, and the denominator corresponds to mod A and mod of B, and this is what is actually your dice coefficient, and 1 minus dice coefficient per class gives you the loss within the class, and if I take the sum of loss over all the classes, this gives me the overall segmentation loss, and during training using backpropagation and gradient descent operation, you can try to minimize this loss. So, your training operation will be such that you modify the network parameters following the gradient descent, where the gradient of this loss function with respect to parameters will be taken, and you modify the parameters in such a way that this loss function is minimized. So, for training of the neural network, which is meant for semantic segmentation, either you can use that pixel wise cross entropy loss, or I can also use this dice loss for training of the neural network. Okay. Now, given this, now I want to move to another application of this deconvolutional neural networks. The application is image restoration or noise filtering. And for doing that, what I need to understand is that what is an image degradation model and why do I need filtering operation. So, let us look at this. Any image capturing operation follows through, goes to this degradation steps. So, suppose my actual input image is fxy, this fxy goes to a degradation function which is h, as shown over here. So, I have my actual original input image which is h, this is a degradation operator, and after degradation operator I have an additive noise. So, at the output of this block I get an image gxy which is degraded and noisy image. So, the purpose of this restoration is to remove this noise and the degradation, and in classical image processing operations there are various techniques for performing this task or for restoration. This is what is known as restoration. So, the purpose of restoration is that I want to have an output image which is very close to my original input image fxy. And you find that in this case, if your degradation operator h, this becomes an identity operator, then your degradation model is simply additive noise added to your input image. So, the image that we get is a noisy image, and in that case this restoration operation simply becomes a noise filtering operation. I do not have to consider what is my degradation operator or degradation filter. So, in today's lecture, what we will talk about is how we can employ a neural network, a deep neural network or convolutional neural network for performing this image filtering operation or noise filtering operation. Now, you find that when I have discussed about the training of the neural network, you find that in most of the cases the architecture of the neural network is same, whether you use it for classification purpose or whether you use the neural network for segmentation purpose or you use the neural network for even noise filtering purpose. What makes the functions different is how you train your neural network. That means how you generate your ground truth images or the images that is meant for supervised training of the deep neural network, and how you define your loss function. Your training algorithm is same, it is the same backpropagation algorithm using gradient descent. So, what are your training sets and what is your loss function? These two actually decides that what will be the function of the neural network, how the neural network will behave. So, let us see that how you can use the neural network for noise filtering operation. So, by noise filtering what I mean is, here on the input on the left hand side we have an image which is corrupted with additive Gaussian noise. So, you find that what is the nature of the image or what is the characteristic of the image that is on the left hand side, which is a noisy image. By filtering, what I mean is I want to remove this noise so that I get a clean image, and the clean image as shown on the right hand side. Obviously, the image that you have on the right hand side, that is much better than your noisy image what you have on the left. So, I want that my neural network should perform this similar task, that is this noise filtering operation. So, let us see how we can do it. So, a neural network which has been suggested as suggested by the authors of this paper, which is an image restoration network. So, this image restoration network, it is a deconvolution network where I have arrays of the convolution networks followed by an arrays of a set of deconvolution networks. And this particular network, the deconvolution network, also makes use the concept of the skip connection. That is, from a convolution layer, you can directly feed the output of the convolution layer to the corresponding deconvolution layer, the peer deconvolution layer in the deconvolution part. And these are the skip connections that is shown over here. So, these are the skip connections that you can have. So, you find that from the convolution layer, you can have a skip connection to the deconvolution layer. So, this is the in general the architecture of the network that is used for image restoration or noise filtering purpose. Now, what does this convolution layers and the deconvolution layers that actually do? You find that in this particular case, the convolution and deconvolution, they have mirror symmetry, right? The number of convolution layers and the number of deconvolution layers, they are same. The way it is reduced on the convolution side, just in the inverse way, the size is increased in the deconvolution side. Now, what does this convolution layer do? As we have seen before, that when you perform a convolution operation, the convolution operator tries to extract some abstract information or the features of the input image. And when you perform the deconvolution tries to upsample these abstract information which is collected by the convolution layers, and by upsampling this information is being restored back to its original resolution. So, the operation of the convolution layer and the operation of the deconvolution layer, they are just opposite. So, the convolution layer acts as the feature extractor, and while it tries to extract the features, in the process it eliminates the noise or the corruptions which are present within the input image. And when you perform the deconvolution operation, as the noise has been removed or has been suppressed by the convolution operator, when I try to deconvolve or upsample the input image, I restore the original size, try to restore the original resolution of the image, but because the noise was suppressed by my convolution operator, when I restore the original resolution, it will be the noise will be removed from that original resolution. So, you find that when you perform the convolution operation, along with the removal of the noise, the convolution operator will also remove certain features or the detailed information which is present in the image. So, as a result, when you perform the deconvolution operation, your original restored image or the original resolution image, though it will be free of the noise, at the same time, because the convolution layer has removed finer details of the image, those finer details will also be lost from your restored image. And that is where your skip connection plays a very, very important role. So, let us see over here what this skip connection does. As we have seen that because the skip connection, output of a convolution layer is directly added to a deconvolution layer, the corresponding deconvolution layer. The convolution layers which are in the shallower part, for them the removal of the detailed information of the image will not be that severe. But as you move inside the deeper layers, the detailed information will be lost more and more. So, using the skip connections, what you are doing is, when you are trying to deconvolve the image or trying to restore its original resolution, you are actually skipping all the intermediate layers, and you are getting the detailed information of the corresponding convolution layer and feeding it directly to the deconvolution layer. So, when the deconvolution layer tries to upsample the image, it will get that detailed information from its peer convolution layer. So, in the upsampled image, it will try to retain that information which it receives from the peer convolution layer. That is how the detailed information in your restored image will also be maintained. The skip connection also helps in the backpropagation algorithm that we have seen earlier, that when the network becomes very deep or the number of layers is very large, in that case what happens is that it suffers from a problem which is known as vanishing gradient problem. So, this skip connection that helps to solve or to avoid that vanishing gradient problem during the training of the neural network. Now, when you have this deconvolution network, the authors of these papers, they have suggested the architecture of the image restoration network, or the block of the image restoration network is something like this. So, you find that I have a deconvolution layer, say D4, and the corresponding convolution layer is C1. Corresponding to C1, which is a convolution layer, I have the corresponding deconvolution layer D3. So, I can have a skip connection from C1 to D4, I can have a skip connection from C2 to D3 and so on. So, when I have this skip connection, the skip connection is in between the peer layers of the corresponding layers. The authors have also compared the output, compared the performance of their network with some other networks, say the networks which are fully convolutional networks. So, they have compared their result, their performance with fully convolutional networks having 5 convolution layers and 5 convolutional upsampling layers, a network with 10 convolutional layers and 10 convolution upsampling layers. And the authors have suggested a deconvolution layer with deconvolution network with 5 convolution layers and 5 deconvolution layers. And as is shown in this plot, that the performance of this deconvolution network with 5 convolution layers and 5 deconvolution layers is much better compared to competing fully convolution layers. It is better in terms of PSNR of the restored image. So, the other application, and here you find that how this skip connection network improves the performance or improves the quality of the reconstructed image. Here you find that over here what we have is the noisy image, and this is a restored image where skip connection was not used. So, here you find that as we said before, that skip connection actually feeds the details information of the image which are available in shallower layers of the convolution part to its counter deconvolution network, deconvolution layer, so that when the deconvolution layer tries to restore the image to its original resolution, the detailed image information will also be available. And if I don't use such skip connections, this detailed image information will be lost. And that is what has been shown over here. So, this is the output without skip connection, and this is the output that you get with skip connection. And if you compare these two restored images, it is quite obvious that the quality of the image that you get with skip connection is much better than the quality of the image that you get without skip connection. Simply convolution, deconvolution layers, but there is no skip connection operation. And it is also visible in terms of improved PSNR. you find that without skip connection the PSNR is very poor, and when you use the skip connection the PSNR value is quite large. So, this skip connection helps both for improvement of the quality of the restored image as well as it helps in training of the neural network. Now, again the most important part, as we said, that how do you train this neural network, and as we said that for training of this neural network I need the ground truth. That means I have to have an input noisy image and I have to have the corresponding clean image. So, the way you try to train your neural network is you feed the input to the neural network. At the output of the deconvolution layer, at the final output layer, you get the reconstructed image or the restored image. I want that restored image should be same as the clean image, and this noisy and clean image pair is used for training of this neural network. So, you compute what is the error between the reconstructed image and the clean image, and using backpropagation and gradient descent you try to minimize this error. So, the error function in this case will be something like this. So, my input pair is xi yi, where xi is the noisy image and yi is the clean image, and what my network gives is a function of xi and theta, where theta is the network parameter, and my loss function is f xi theta minus yi, where yi is the clean image, and this f xi is the restored image restored by the neural network, xi being the noisy image and yi is the corresponding clean image. You compute what is the error between these two, and sum of these errors over all the training images, that gives you the loss function, which is L theta. Theta is the network parameter, and then you try to minimize this loss function iteratively using your gradient descent approach, backpropagation approach to update the network parameters theta, and that is how the network is to be trained. And once the network is trained, then given an input noisy image, the network will give you an output image which is a clean image or the noise filtered image. There are other applications as has been suggested over the same approach is in low dose CT denoising. You find that when you compute, when you take the X-ray CT images, if you increase the X-ray energy or the dose, then your image will become clean. But if you reduce the radiation energy, the image will be noisy, as is shown over here. So, you can use the similar technique, similar denoising technique using the deep convolution, deconvolution networks for cleaning these images. So, this example shows that again for training purpose I need the clean low dose image and the high dose image pair, clean image and noise image pair for training of the network. And once the network is trained, and this is the architecture of the network that can be used for this denoising purpose, which is same as that skip connection network. And this is one of an example result, that on the left hand side what you have is a low dose CT image. This is the normal CT image, and in the middle what you have a CT image which is restored by a trained deep neural network. The advantage is that if you have a low dose image, then many of the nodules in the image may be missing, which may create a problem for diagnosis based on the CT images. So, once you have a cleaned image, then the diagnosis becomes much more reliable. So, in today's lecture, we have talked about one of the loss functions, that is the dice loss, which can be used for training a neural network meant for the semantic segmentation purpose. And we have talked about another application of this deep neural network, which is for denoising of the noisy image. So, with this we will stop our discussion on the discriminative networks. In our next class, we'll start talking about the generative network. As we said that your deep learning is there are two different aspects. One is for classification aspect, which is the discriminating network, and the other one is generating aspect, which is done by generative network or generative learning. So in our next class, we'll talk about how we can have a generative neural network. Thank you.